In this example, we're going to calculate the exit temperature of a flow moving through a throttling device. We're given that we have a steady flow of ammonia and a throttling device. These devices generally operate to reduce the pressure in a system, but they do so while maintaining the specific enthalpy. So you can imagine that if P decreases, the other term involving internal energy would increase. And we're given in this case that the inflow pressure is 16 bar, the inflow temperature is 100 degrees C, and we're also told that the exit pressure is 4 bar and we want to calculate the exit temperature. We can use the lookup tables in the back of your book for the inflow conditions to find the specific enthalpy, and we see that H sub I equals 1644.56 kilojoules per kilogram. Because it's a throttling device, we know that H is conserved, so we also know that the exit specific enthalpy must have the same numerical value. Now I'm actually going to do this problem using the lookup tables from your book first, and then at the end I'll go back through and use NIST to show you that you get approximately the same answer. So our goal is to use the lookup tables to figure out the temperature, knowing that the pressure is 4 bar and the specific enthalpy is 1644.56 kilojoules per kilogram. But we can anticipate that we're not going to find exactly that specific enthalpy, so this will probably be an interpolation problem. If you look in the back of the book, you can see that superheated ammonia vapor does have specific enthalpies around this range for that pressure, so what we can do is find two values at two different temperatures and then do an interpolation to figure out the exact exit temperature that we want. Let me show you. So if we look in the back of your book at superheated ammonia, we find that at 100 degrees C and 4 bar, the specific enthalpy is 1682.58 kilojoules per kilogram. At the same pressure, but at 80 Celsius, we find that it's 1636.41. Those two values bracket the specific enthalpy that we're interested in, so now we can do an interpolation. And I'll actually walk through the steps to remind you how this works. So we know that the difference between the specific enthalpy at 100 C and 80 C divided by the actual temperatures, 100 minus 80 C, must be equal to the exit specific enthalpy minus the value at 80 C divided by the exit temperature minus 80 C. So we can rework this to solve for the exit temperature, and that's not too complicated. And we get this expression, and now we can just plug in our numbers because we know everything on the right-hand side. We found it all in the lookup table, or in the case of the specific enthalpy at the exit, we knew it because it was the same as the inlet value. So we put those numbers in, simplify this, and we find that the exit temperature, according to this approach, is 83.5 degrees Celsius. Now let's perform our usual sanity check. We know that we were interpolating between temperatures of 100 and 80, so indeed this value is between those, and you can also see that the target specific enthalpy value was a little bit closer to the value corresponding to 80 C, and indeed our exit temperature is a little bit closer to 80 than it is to 100, so everything makes sense. Now we're going to do this problem again using NIST, and the reason that I want to do that is to illustrate that we're going to get approximately the same answer with different numerical values of the specific enthalpy. That may seem worrisome, but actually physically, every time we've used the specific enthalpy in this course, we've only been taking differences. So as long as the differences are preserved, the absolute value doesn't matter. The reason for this is that the textbook and NIST use different zero points for the specific internal energy, and that affects the specific enthalpy since H equals U plus PV. Again, that just illustrates that we're really only physically interested in delta H and delta U. Okay, let's go through this. So I'm going to clear out the stuff on the side, and we'll clear out the data from our book. Now remember, you can't look up the inlet value in your book and then look up the exit value on NIST because you're mixing and matching different zero points. So I'm going to assume you can handle this step on your own. It's not that exciting to watch. Let's use NIST. We'll look up the inlet pressure and inlet temperature, and we find now that the inlet specific enthalpy is 1807 kilojoules per kilogram. So we automatically know for a throttling device that our exit specific enthalpy has to have the same numerical value, 1807 kilojoules per kilogram. Now our goal is to use NIST to look up the pressure, that specific enthalpy, and see what temperature we get. So we go to NIST, and I'll show you what I see on my screen. Here we go. All right, so we want to look up ammonia. And there it is. And we'll select Celsius, bar, kilograms per cubic meter, and kilojoules per kilogram. Let's do isobaric properties since we know the pressure. Okay, and so I said that the pressure was 4 bar. For the temperature range, let's select a wide range, assuming that we don't know the exact value. Let's go between 50 and 100 C, and then we'll do a pretty small increment so that we ought to be able to get close to our H value without having to do any other interpolation. Okay, and let's just look at it as an HTML table. So the idea is I'm going to scan through the specific enthalpy until we find our value of about 1807 kilojoules per kilogram. So we do that. Scroll, scroll, scroll. And here we are. So this is pretty close. We have 1807, and now we see the corresponding temperature is 83.4 degrees Celsius. So we were off by zero point 0.1 Celsius, but all things considered, we've got a better uncertainty than 1%, and we used a different resource and had a totally different value for the specific enthalpy. You can see that physically, though, we got about the same temperature, and that was the point of this exercise. So again, when doing problems like this, make sure you don't mix and match between textbook values and NIST values. As long as you stick to one resource or the other, though, you should get the same physical outcomes.